Hi, this is TheoryStation. I'm John Duggan. The program is Rational Choice Modeling. The series that we're in is the Basic Formal Theory Toolkit. This is installment 15 in the series. So I've been talking a lot about public good provision, partly because we've kind of built up our toolkit a bit, and partly because it's just such an interesting model to work with. In the last installment, I solved for this equilibrium activity level of these two decision makers. And then I went through an example with a natural log benefit function and linear cost. And I argued, or I stated at the end, that that the equilibrium activity levels were Pareto inefficient because the two decision makers, their decisions didn't reflect the externality they were imposing on the other person. So what I want to do now is just state that, or argue that in a little more rigorous way, and also give some of the geometric intuition behind it. Okay, so maybe to begin with, we can just go back to the example. Well, first, let me just note that this is public good provision. Continued. And in our example, we had this, the benefit function was just the log, natural log. And cost function was just linear gamma times x, where gamma is a positive parameter. And so the, let me do it up here. The equation that characterizes the equilibrium activity level in this model in general is this expression here. And in the example, that just reduced to and then we solved for x bar, and that was just this expression here. Okay. One way to see, just in this little example, that that these guys are choosing an inefficiently low activity level is, well, let's think about the equilibrium net benefit of one of these decision makers. Okay. So in general, the equilibrium net benefit, let me do that up here. That's just the benefit when I'm choosing x bar and you're choosing x bar minus the cost by choosing x bar. So that's the equilibrium net benefit in this public good provision problem. Well, so we can look at that equilibrium net benefit expression and say, what happens if we increase x bar, if we increase the activity level of both of these guys, okay? So, we can just do that in a general way by taking the derivative of that with respect to x bar. All right, so we're going to differentiate this. With respect to x bar, the whole thing. Well, that's going to be marginal benefit times 1 plus beta minus c prime x bar. And, right, so this expression here, that's going to tell us how the net benefits of these two decision makers change as they both increase their activity level, okay? And I'm going to argue that, that's positive. In this example, you can just see that directly by plugging in, right? So in the example, you know, the marginal benefit is just the log, so that would be 1 over 1 plus beta times x bar, and we're multiplying by 1 plus beta here. Okay, the cost is linear, so the marginal cost is just gamma, but of course the 1 plus betas, those cancel out. Okay, so this this just reduces to 1 over x bar minus gamma. So in our example, this expression gives us the rate of change of net benefit for both these guys if we were to increase x bar for both of them. I claim that that's positive, and you can just plug in our expression for x bar. We already solved for that equilibrium effort level. You can plug that into this derivative, right? So that's 1 over but that's just 1 plus beta times gamma minus gamma. Now, remember, if beta is equal to 0, there's no externality, so there's nothing to be done. But when beta is positive, this thing is equal to beta times gamma. That's positive. So that's how, you know, we can show in this example that both decision makers could be better off if they just could both increase their activity levels. Obviously, the weird thing about that is that conceptually they could. There's no problem with them increasing their activity levels. It's just that they don't have the incentive to do so. Right? If the other guy were increasing their activity level, then I would just want to decrease mine. Okay, so let's talk about this in general now. I want to argue that that in general, in this kind of situation, the equilibrium activity levels are going to be inefficiently low. So to do that, I'm going to consider a similar maximization problem where I'm going to choose x to maximize the benefit of 1 plus beta times x minus the cost of x. Okay. We've seen, you know, other maximization problems, and this looks kind of like the one that the decision maker was solving in equilibrium, but it's different, right? So decision maker 1, for example, was maximizing with respect to x1. Okay, so that was kind of similar looking. An important difference, though, in equilibrium, this x1 isn't multiplied by anything because the decision maker in equilibrium is not taking into account these externalities they're imposing on the other person or generating for the other person. In this new problem, the x here is being multiplied by 1 plus beta. Okay, so our problem here is reflecting the externality in a way that the decision maker's problems were not. Okay, so this new problem, with the structure we're imposing on this, will have at most one solution. There's very standard structure that will, you know, ensure that there is at least one, and I'm not going to worry about that part. Basically, this thing's going to have a unique solution and let's use the notation x with the superscript star. All right, that has a unique solution. It's going to be strictly positive, again, under standard assumptions. So it's going to solve the first order condition for this problem, which is we're going to differentiate this objective function with respect to x, and we get this marginal benefit times 1 plus beta equals c prime x. Okay. All right. Let's go back. That might look a little bit familiar. It looks a little bit like the equation that characterizes the equilibrium effort level, which was this. Okay, but it's different, right? Because here we have this 1 plus beta factor on the left-hand side, and here there's nothing, okay? Because in equilibrium, the choices of the decision makers don't reflect the externality. All right, so I'm going to argue that that this unique solution, this x star, is it's bigger than x bar. And then I'm going to argue that if both decision makers could, if we could convince both decision makers to increase their activity levels to this x star, they would both be better off. Okay, so first, why is x star bigger than x bar? Well, let's go back to our picture of equilibrium with the marginal benefit and marginal cost curves crossing. So marginal cost was some function like this. Marginal benefit, remember we were talking about marginal benefit evaluated at 1 plus beta times x. Okay. The equilibrium activity level was determined by the intersection of those graphs. That gave us our x bar. Okay. But now I want to think about x star. So if we look at the equation for x star, the right-hand side is the same as before. It's the marginal cost. But the left-hand side is it's this marginal benefit function, but scaled up by 1 plus beta. So that x star is then where the blue graph and the marginal cost curve intersect. And you can just see geometrically that when we increase the marginal benefit function by this factor of 1 plus beta, that's going to increase the, it's going to shift up the marginal benefit function. And then that intersection is going to have to move to the right. Okay, so x star is strictly bigger than x bar. But now I just want to, mention that, or I want to point out that if both of these guys increase their activity level to x star, they would both be better off. So why is that? So the equilibrium net benefit was the benefit, it was the benefit of my own plus what I get from the other guy's activity level minus the cost of mine. So this was the equilibrium net benefit, right? Okay, but this right here Well, that's just the objective function evaluated at x bar. Okay? But we've shown that x bar does not maximize that function. X star does. X star is bigger. Okay? So, because of that, it just follows, if both these guys chose x star, so we evaluated this at x star instead of x bar, that net benefit would be bigger. All right, and so this just shows that under the pretty general assumptions that we're maintaining, that we get this kind of under provision of contribution to the public good. We could see it explicitly in the example, but it's not just an artifact of that example. It's much more general. All right, I said I wanted to go through some of the geometry behind this, and I do think it's kind of fun to do that. First of all, let's think about what these net benefit functions look like. Okay, the net benefit function is it's this. If I'm person 1, for example, given that the other guy is doing x2, my net benefit is just this expression here, right? I get the benefit of my own activity plus beta times the other guy's minus the cost of mine. So you can think of this as a utility function. It's a function of x1 and x2. So we are actually in a multi-dimensional policy choice model. It's just that the policy positions now are actually activity levels. But mathematically, it has that two-dimensional structure. And so I can graph this net benefit function in this three-dimensional space where, the activity levels span a Cartesian plane, and I lay that flat, and then I use the vertical axis for net benefit. What would the graph of a function, of a net benefit function look like? Well, let's approach it systematically. Suppose this x2 is 0, the other guy is not doing anything. Then person 1 can choose any level of x1, and if I were to graph what their net benefit might look like, it's going to increase at first, and then there's some optimal amount of, there's some level of x1 that maximizes that guy's net benefit. On the other hand, if we, suppose we set x1 equal to 0 and increase x2, so this term would just disappear, and there's no, cost is just a constant. Then we just increase x2. That's just going to increase person 1's benefit with no cost. So if I were to graph their benefit, if we, as we increase x2, it's just going to go up and up and up. Okay, and it's going to have that concave shape, but okay. What does the rest of this look like? Well, for different levels of x2, like this one, let me just draw something here. Let's go up here. The graph of this net benefit function above this line, again, it's going to go up and then down. Same here. It'll go up and then down. Like that. And then something like this. All right, kind of messy to look at, I suppose. All right. Now, we've talked about how these 3D graphs are not the easiest to look at, and it's better to look at what we call indifference curves in the two-dimensional model. So what would an indifference curve look like here for person 1? Well, that's going to be for a certain utility level or level of net benefit, that's going to be the x1, x2 pairs that generate that net benefit. Okay, so if we think, for example, about this level of net benefit, I can go over here to the vertical axis. Here, it's this level. What would that, now just imagine starting at this point here on this hill and then walking around the hill, but maintaining that altitude. What would that curve look like? Well, it's going to come around like this and then like so. And all of these are going to have this kind of shape. And in my picture down here, that's going to, those will look like this. That would be, for example, a locus of x1, x2 pairs that generate a given net benefit for person 1. That's not the great looking. Let's do it more like this. Okay. All right, so what does an equilibrium look like in this model? Well, we know two things about it. One is, from person 1's point of view, they have to be choosing x1 optimally, given that person 2 is choosing their level. All right, so suppose person 2 is choosing this amount of this activity level, this x2 here. Think about what person 1's maximization problem is. They're taking x2 as given. They can't affect that, but they can choose x1. They can choose 0 or make it bigger. So essentially, they can choose anything on this this bold line here, and they're going to choose the best thing they can. Okay. Now, in this problem, you can see that indifference curves that are higher up represent higher levels of net benefit. So the highest, given that person 2 is choosing x2 in this picture, this indifference curve here that I've highlighted is the highest attainable indifference curve. Okay. And there's a unique choice of x1 that will generate that highest possible net benefit, and it's this one right here. So given this x2, the optimal x1 is this. Okay? You can actually think of this as like solving a constrained optimization problem, but remember, they're both doing this. They're doing this simultaneously. So in equilibrium, we know they're both choosing this optimal level, and we've argued that the equilibrium is symmetric, so the optimal level, this optimum choice for them, is the same. So it's going to lie on the 45-degree line. Let's suppose it's this right here, somewhere on there. Since person 2, well, let's see. Person 2 is choosing x bar, person 1's choosing x bar, but remember, person 1's choice must be optimal. given that person 2 is choosing X bar, what are the combinations, what are the pairs of activity levels that person 1 can choose? Well, person 2 is doing X bar. There's nothing person 1 can do about that, but person 1 can choose anything on this horizontal line here. Okay. In equilibrium, they're choosing optimally, and so we know their indifference curve looks something like this. Okay, there's this tangency. It's, you know, we've seen this come up in other situations, but the idea of a tangency is quite important here. This is from person 1's perspective. For person 2, it's flipped around. Person 2 takes x1, or takes 1's activity level as fixed at x bar and can choose any x2. So they can choose anything on this vertical line. Now, their indifference curves are the same as person 1's, but just reoriented from their perspective. And so they're going to have a tangency as well. And their indifference curve will look something like this. Okay. Now, notice that each person is optimizing individually. We have these tangency conditions for both guys. Okay. But when we look at the big picture, and we think about, you know, varying the activity levels of both guys along the 45-degree line, we can see that we've created this lens. And as we talked about in the multidimensional policy model, Pareto optimality is inconsistent with something like this. If a pair of positions generate a lens like this, that means we can move into that lens and choose positions that increase the utility of both decision makers. And that's why, you know, that's sort of the geometry behind the Pareto inefficiency of equilibrium outcomes in the public good provision model. All right, so that is a lot on public good provision. I'm done with that for now. I do want to pick up one more topic in the next installment, and that will be going back to the one-dimensional policy choice model, but adding an element of uncertainty, which is, well, we're not spending too much time on it, but it's a very fundamental aspect of politics and really life in general. There's a huge branch of formal modeling that's designed to deal with that and help us understand choice under uncertainty. So that's what's coming up next. I'll see you there.